All right, hello everyone. So we are going to continue on with chapter 3. So I was going to go over the test, but I didn't realize that the format of the test, because it's online, every question is different in every order for every student, and all the answers are different. But you should be able to see which ones you got wrong, and you should be able to see what the correct answer is. So what I'm going to do instead is have you guys go through your exams on your own. And then if you find that there are questions that you are specifically having trouble with, or I can also look at the questions and see which ones like a lot of you guys got wrong, and I can specifically go over those. But to go over the test, it's going to be more confusing than not at this point. So go ahead and do that, and then next week, if you guys have questions, I can answer them as a class or individually. And again, yeah, I'll look for the ones that were like 80% of the class got wrong. Okay, so we left off talking about starting to talk about stoichiometry. Oh no, did I just exit that? I believe we were just finished. We had just talked about calculating the mass for an atomic formula. So we will get back to that, but I want to rewind just a little bit back to balancing equations, because you may end up finding that some of the equations that you need to balance are in like a word form. So we'll do an example together. All right, so I want you to write a balanced equation for sodium combines with chlorine to form sodium chloride. So I want you to write an equation for that, and then I want you to balance it. Another 30 seconds. This one shouldn't be too challenging. Okay. So when you're going from a word, what would be a word problem, to a balanced equation, I will sometimes underline all the different things that I need to take into account. So I have sodium. It's going to combine with chlorine to form chloride. And if you want, you can circle to form. That is going to be your arrow. You can, give a squiggly line to the word combine, just so that you're starting to see how this can be represented in a chemical equation. So the first thing I'm going to write is sodium. So the symbol for sodium is Na. Sometimes these will give you the state, like it'll say solid sodium, so you'd want to put like a little S there. If it doesn't give you the state, that's okay. You don't have to put it in. So we have sodium. You always want to be asking yourself, is this a diatomic molecule? So sodium isn't a diatomic molecule, so we'll just keep it as Na. Combined. So combining means I'm going to add chlorine, which is Cl. Now chlorine is a diatomic, so I'm going to need to put a 2 in there. If you don't put the 2 in there, it'll throw off your balancing. So to form, to produce, to create, decomposes to, right? That's the arrow. And then we want to produce sodium chloride. Sodium chloride is a metal combined with a nonmetal. So sodium is Na plus, chlorine is Cl minus, flip flop, and we should end up with NaCl. Now, if you notice, if you forgot the diatomic, you would have this and you would look at it and say, well, that's already balanced, but it's not. So because we've got the 2 there, it changes these. We've got 1, 2, 1, 1. So I'm going to put a 2 in front of this. That changes this to 2, changes this to 2. And now we've got to throw a 2 in front of the sodium. Okay. So make sure you're including your diatomics because you guys can be tricky. We'll do a couple more of these where they're word problems. The practice sheet had a couple good ones. Okay, I gotta open that for us. The guided notes. Okay, so looking here, there's 3 of them. So I want you to try all 3 of them. Okay, I'll give you about 6, 7 minutes, 2 minutes apiece. So it's this right here. So practice, we're going to write balanced chemical equations for the following reactions. So the first one says solid mercury 2 sulfide decomposes into its component elements when heated. All right, so you're going to write a formula for that, and then you're going to balance it. The next one, the surface of aluminum metal undergoes a combination reaction with oxygen in the air. And then the final one is related to a combustion reaction. You should know the products of a combustion reaction. So I'm just going to give you guys a try, just see how it works. It does require you to use some of your nomenclature stuff from the last chapter, which nomenclature is not going to go away. So just keep practicing it.
I have a question.
Yeah, what's up?
So how do we know if it's diatomic?
How do you know if it's diatomic? You have to have it memorized. Yeah.
Okay. Are they in the book somewhere?
They are in the book, and they have no fear of ice cold beer. So hydrogen.
Okay.
Go from hydrogen, come over to nitrogen. So we've got hydrogen, nitrogen, oxygen, fluorine. You see how we go in an upside down L, and then drop down all the way to iodine.
Okay.
Okay, so hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Those are all diatomic.
Okay, I got it.
Anything
awesome.
else?
Thank you.
Not a diatomic. Yeah.
Okay.
Okay. So the first thing that we're going to want to do is identify what we need to be writing on each side. Right, so this is a reactant. It decomposes. I know that that's behaving as my arrow into its component elements. So its component elements would be mercury and sulfur. So the first thing is to write a formula for mercury 2 sulfide. When you're dealing with mercury 2 sulfide, we've got mercury, which is symbol Mg, and that has a 2+ charge. Why? Because it's giving me the 2+ there. Sulfur always has a 2- charge. So when we flip-flop those, it should end up being MgS balanced, right? It'd be 2 and 2, and so you produce it. So if you can't go from this to this, it's going to be troublesome for balancing the equation. This does say that it's a solid, so I guess I can throw a little S in there too. All right, it decomposes. So I'm going to put my arrow, and then I'm going to break it apart into magnesium and sulfur. Sorry, I don't know why I keep putting magnesium, mercury. My bad. My bad. Hg, that's what I wanted. Okay. Let's give it Hg with a 2+. So this thing will be HgS. So we're going to break that into its components, which will be mercury, Hg, and sulfur, which is S. Are either of these diatomic molecules? They are not, so we do not have to worry about putting a 2 in there. So the thing is actually balanced just the way it is. So we can leave it at that. All right. Any questions on that one? It was pretty simple. You got a question, speak up.
Can you just give a little bit more info on why you didn't use the 2? So if it's a diatomic, you just don't use the Roman?
I'm sorry, what was that?
So you didn't use the 2 for what reason?
The 2 and the 2?
And the mercury 2 sulfide.
Why I didn't call it mercury 2 sulfide?
Why didn't you put the 2 in the chemical equation?
The 2 is talking about the charge, not how many you have.
Okay.
Yeah, that's super, super common mix up. This 2 is telling me that I'm dealing with mercury, Hg, with a 2+ charge. It says, it doesn't tell you anything about how many you have, okay? So you have to write it with the charge, and then from there you go ahead and balance.
Okay.
Does that make more sense?
Yes.
Okay, so if I have something like copper 3, it does not mean I have 3 coppers. It means that I'm dealing with, ooh, it means I'm dealing with copper with a 3+.
Okay.
Okay.
So when you're writing a chemical equation, it just doesn't come into effect at all, ever?
What doesn't, this number?
Yeah.
I mean, it does in that you have to have the right charge to flip-flop to get the right formula.
Mm-hmm.
Because if this was mercury, let's say instead of mercury 2, this was mercury 1. Mercury 1 would be Hg with a 1+ charge. That would be sulfur with a 2-. I'm sorry, I don't know why this thing is giving me such a hard time. That would then be Hg2S. That would be the formula, different than this one.
Okay.
Okay. So this, it's not written in here, but it affects what will be written here.
Is it common that they don't cancel out? Will that happen to us a lot? Or will it normally be?
You'll have times where the charges don't cancel, and you'll have times where the charges do cancel. In this case, the charges didn't cancel, right? You get a 2 and a 1. Anytime though you have a 2 and a 2 or a 3 and a 3, they cancel out to 1 to 1. Good? Okay. All right, so the next one, the surface of aluminum metal undergoes a combination reaction. So I've got aluminum metal undergoes a combination reaction with oxygen in the air. Okay, so I'm taking aluminum and I'm going to combine it with oxygen. So aluminum is Al. I'm combining it with oxygen. Oxygen is a diatomic. So we're going to put that as O2. And then we've got to figure out what its product is. Well, when it combines together, we get aluminum oxide. This is where we have to balance charges, right? So aluminum has a 3+ charge, oxygen has a 2- charge. Flip flop, Al2O3. So Al2O3. So you don't want to just smush them together. You've got to charge balance them if it's a metal and a non-metal. So from here, I can go ahead and balance it out. This is a multiplier of 2, so I'm going to put a 2 right there. So that means 6 oxygen. So I can put a 3 here, 4 there for aluminum. Questions on that one? Okay, last guy. Write the balanced equation for the reaction that occurs with ethanol. So here's ethanol, and it's burned in the air. Anytime you hear something say burned in the air or combusted or set on fire or things like that, that's talking about a combustion reaction. So the rule of thumb is always you write your hydrocarbon, C2H5OH. We're going to combine this with oxygen. It always combines with oxygen, O2. And what are my products in a combustion reaction? Always H2O and CO2. Okay, so CO2 plus H2O. So yeah, you can actually get this from having just a very little bit of information. I could have said, write the balanced equation that occurs when methane is burned in air. And if you have the formula for methane, you should be good to do it because it's always going to be the same thing. The final step here is to just balance it out. So looking over here, I've got 2 carbons. So we balance carbons first. So I'm going to put a 2 there. Then we need to balance our hydrogens. You got to take into account all hydrogens, all right? So there's 5 hydrogens here, and then there's a 6th hydrogen there. So there's 6 hydrogens on this side. There's only 2 hydrogens on this side. So if I put a 3 in front of there, that should balance my hydrogens. Now I've got to fine tune my oxygens. So on this side, I have 4 oxygens, 7 oxygens. So oxygen is 7 on this side. On this side right now, oxygen is 3. So I'm not going to mess with this because if I put a coefficient in front of this, what's it going to do? It's going to change my carbon and it's going to change my hydrogen. We don't want to do that. So let's go over to this side. If we put a 3 here, that's going to change this to 6 oxygens. And then plus this gives me the 7 oxygens. And we're balanced.
Okay, so a combustion reaction is always going to be adding O2 to whatever your hydrocarbon.
Yes, yes. So just get in your brain, like you're going to have a hydrocarbon that's given to you. It could be methane, ethane, propane, whatever. If it says that it burns or combusts, you combine it with oxygen and you spit out CO2 and H2O. And heat, obviously. That's why we burn the stuff. So that we can produce energy. But yeah. Okay. Any other questions on working on that? So it's just, you gotta remember your nomenclature. You gotta remember how to name stuff. That I think is the hardest part. It's not even the balancing, it's getting from this into, getting from the words into this. Okay, so I'm gonna clear this out. While we're here, let's find the formula weights for these. Well, go back to the slides for a sec. So we had talked about formula weight and how you have to add each of the individual atoms' masses together to get the total weight. Molecular weight, we'll get into that in a second. Okay, so let's do the formula weight for the 2 that were on that sheet there. So we've got CaCl2, and then we've got Ca3PO4 2. So I'm going to transfer those over to my whiteboard because it's hard to read them here. So we've got what? Calcium chloride and calcium phosphate. Calcium chloride and calcium phosphate. So go ahead and figure out the masses for each of those molecules. You will need a periodic chart and a calculator. Someone's got their mic on. Just heard someone come in.
Accidentally clicked. Sorry. Ignore my brother.
Oh, brothers. Brittany, I think that's like the tiniest periodic chart I've ever seen.
I'm pretty annoyed with it. We ordered it thinking it was like an 8 by 11 and it came in and
Yeah, put it up. Oh. Okay, so for this guy here, we're going to need to take the mass of calcium, which we have as 40.08, and we've got one of them. And I need to add it to my chlorine, which is 35.45, and we have 2 of them. So always make sure you're taking into account what the subscript is. So when I take this and I add it to these 2 multiplied, I should end up with 110.98 AMU. If you had 111, that's okay. It's close enough. You will find that certain texts, homework, things like that are more or less anal about how many decimals they use. This guy over here is a little bit more complicated. So we do have calcium again. So I've got that 40.08. I need to multiply it by 3 though. All right. Now the other things I have phosphorus and I have oxygen. So the mass on phosphorus is going to be 30.9, what is it, 99? Now, how many of those do I have? Well, this 2 is getting distributed to both components within the parentheses, right? That's why they're in the parentheses. So I should actually have 2 phosphoruses. The last thing is oxygen, which has an atomic mass of 16. How many oxygens in total do I have? Well, if I've got 4 inside the parentheses and I've got 2 of these packets, I need to multiply those 2 together. So your value should be multiplied by 8. Any questions on that? This 2 is acting as a multiplier to whatever is inside the parentheses. So when we calculate this one out, it's got a pretty heavy mass. We've got roughly 310.18 AMUs. So as long as you have your periodic chart, it shouldn't give you too much trouble solving these. Okay. So a molecular weight is what's actually happening in the substance or in the molecule. So molecular weight is the sum of the atomic weights of the atoms in a molecule. So if we look, for example, here for glucose, which has a molecular formula of this thing right here. So the molecular formula is going to be some sort of multiplier of the empirical formula or of the formula weight here. So this has 6 carbons, 12 hydrogens, and 6 oxygens. And we'll come back to this molecular weight when we get into calculating the molecular formula. But in this case, you just want to make sure that you're adding all of the values. It's the same setup as the previous one. All right, so percent composition. You can find the percent of mass of a individual element within a compound by using a pretty simple equation. So the percent of the element is equal to the number of atoms. I don't know why it says number of atoms times number of atoms. It should say number of atoms times formula weight divided by the formula weight of the compound times 100. So if I have NaCl and I want to find the percent of Na, the mass percent of Na, I'm going to take the formula weight of Na and I'm going to divide it by the formula weight of NaCl. Or in this case, I'll take, is it 22.9? 22.9, and we multiply this by 100 to get it in percentage. 22.9, my eyes are going on me, 22.99. We divide it by the mass of both of those, which is roughly 58, and we multiply it by 100. Just a second, sorry. So it's roughly 39.6%. So by mass, sodium makes up about 39.6% of the whole molecule by mass. Which makes sense because if you look at the sodium atom, it's smaller and lighter than the chlorine atom. Chlorine has a mass of 35. If I was
should that top part of the formula say the atomic weight of that particular
atom?
Yeah.
Okay, thank you.
Atomic weight, yep, atomic weight. Atomic weight. Thank you. Yeah, so just the weight of whatever the atom is or element that you're trying to find. In this case, we didn't need to multiply it by anything because sodium had a value of 1. Yes, if I make errors like that whilst, please say something. Normally in class, my students will just say, nope, nope, but it's kind of hard. It's more difficult here. So yeah, just chime in and let me know. Okay, so if we're looking at glucose, which the percentage of carbon in glucose, it doesn't even give us the formula for glucose, but we have 6 carbons and the overall mass is 180. So you just take 6 times the mass of the carbon and divide it by the formula mass of glucose. So let's do some other examples of these where we actually have the formula to write them. Okay. So let's have you do B and C. Since hopefully you've already calculated the formula weight from the previous problem, you should be able to do B and C pretty quickly. So find the percentage of chlorine in CaCl and find the percentage of calcium in Ca3PO4. Okay, I'm actually just going to do this on the other slide. That because annotate, not my friend. Okay, so we want to figure out the chlorine mass percent. So percent of chlorine by mass. So we're going to take the mass of chlorine, which is 35.45, multiply it by 2 because we do have 2 of them, right? So there's a lot of chlorine happening in this formula. And then we're going to divide it by the total mass and multiply by 100. So when we plug this into our calculator, you will end up with something like 63.89%. If you don't do the times 100, you'd get 0.6389. That would be an indicator, oh, I got to move the decimal over 2 places to get it into percentage. Over here, so in this one, we want to figure out the mass of, or the mass percent of calcium. So percent of calcium. So this is 3 times our calcium mass, which is the 40.08 over that really heavy mass of 310.18 times 100. Right? And in this case, we get 38.76%. It's not too hard to calculate those. You just take the individual, divide it by the total. Can you go from mass percents and get back into your formula? You actually can, and we'll talk about how to do that later. It takes a little more work though. Okay, so back to the slides. Ooh, Avogadro's number, awesome. Okay, so in a lab setting, we can't work with individual atoms or molecules. They're just too small. So it's kind of like when you're, when a grocery store is, I don't know, inventorying eggs. They don't count the eggs individually. They will count a dozen, right? So I've got 400 dozen sets of eggs. You can think of Avogadro's number sort of as like the chemist's dozen, but it wouldn't really do us justice to count atoms in sets of 12. because it's not big enough. So our setup is going to be 1 mole, which is acting as our chemist dozen, is equal to, these slides are horrible, 6 point should be here, 6.022 times 10 to the 23rd. So 1 mole is equal to 6.022 times 10 to the 23rd. That makes me really angry that they can't even get Avogadro's number right. This applies to anything, okay? So 1 mole of anything is equal to 6.022 times 10 to the 23rd individual pieces of it. So if I say I have 1 mole of carbon, that is like saying I have 6.022 times 10 to the 23rd carbon atoms. If I have, like they have over here, water, if I say I have 1 mole of H2O, that is the same as saying 6.022 times 10 to the 23rd H2O molecules. So the mole tells us something about how many of the individual parts we have. Why is it set at 6.022 times 10 to the 23rd? Because 1 mole is the exact amount of particles found in exactly 12 grams of carbon-12. So if we had carbon-12 and we had exactly 12 grams, we would expect to find this many atoms, and they set it off of that. So this thing looks like a really nifty conversion factor, doesn't it? Anytime we've got one thing equal to another, it becomes a conversion factor, and then we find that all of chemistry is just dimensional analysis, at least Gen Chem 1. So
the would the unit of Avogadro's number be like particles or?
Yeah, it would be particles or pieces, or you kind of fill in whatever it is you're talking about. So if I was to say something about an element, it would be how many atoms I have. If I was talking about a compound, it would be how many molecules I have. Okay. If I said I had 1 mole of eggs, it would be equivalent to 6.022 times 10 to the 23rd eggs, or individual pieces. All right, so it's the simplest identifiable thing you can break it down into. So if you have water, the simplest thing you can break it down into and still be water would be the molecule. Am I good, Brittany? Okay. Before we get into molar mass, I'm gonna go back.
I can't hear you at all. Has anybody else lost sound? I can't hear you, Candace.
I can't hear either.
Same. I couldn't either. Shutting it.
Yeah,
We can hear you now.
okay, good. I don't know what
Got
happened.
you.
Yeah, I think I hit some. Okay, so we're going to use Avogadro's number, the conversion factor, to get this problem here. So how many atoms are in 3.5 moles of iron? So anytime you see something where it's trying to relate atoms or molecules to moles, just write down Avogadro's number. Okay, so in this case, we're dealing with iron. Doesn't really matter when we're going from atoms to moles or moles to atoms, but I'm going to write it out anyway. 1 mole of iron will equal 6.022 times 10 to the 23rd iron atoms. Because iron is an element, the smallest identifiable thing would be an atom. So this is our relationship. So I can set this up in dimensional analysis. I start with my given information here. So 3.5 moles of iron. I'm going to multiply it by Avogadro's number, or I'm going to use this conversion factor to get me into atoms. So I need to put the mole on the bottom. The 1 mole will always go, the 1 will always go with the mole. The 6.022 times 10 to the 23rd will hang out on top here. And the moles of Fe will cancel. So in this case, when we're going in this direction, all we do is multiply the 2 together. Writing this Avogadro's number in your calculator, if you've got a nicer calculator, I would just write it in as 6.022 E or EE sometimes is the key, 23. That's the fastest way to get it in there. And you may see Avogadro's number as 6.02 instead of 6.022. That's fine. You can use that one as well. Okay, and we should end up
Where
with
do you find the E's on the calculator?
what kind of calculator do you have?
The T184.
Okay, I'm so bad right now. I'm using my phone calculator.
So is it just like this over sin, that E?
Yeah, it should
All
be.
right, cool.
Yeah, it should be.
Over sin. Okay, thank you.
Awesome. Thank you, Brittany. All right. So when we plug that in, we end up getting, I'm going to use 2 sig figs. So just 2.1 times 10 to the 24th Fe atoms. So it's not too bad to go between that. Let's try the other direction. So what if instead of giving you moles, I was to give you number of atoms? So how many moles are in 6.75 times 10 to the 26th sulfur atoms? Okay, how many moles are in 6.75 times 10 to the 26 sulfur atoms? No worries, Jason. Okay, so similar problem to the last one, except we're going in the opposite direction. And again, I don't remember, oh, when I'm going this way, I multiply. When I'm going this way, I divide. I just try and set it up in dimensional analysis and have it tell me what to do. So I start with my given, 6.75 times 10 to the 26 sulfur atoms. Okay. When filling in my next thing, I know that I want sulfur atoms on the bottom because I want to get rid of those and I want to go into moles of sulfur. So then I just figure out the relationship. Well, a mole of anything is equal to 6.022 times 10 to the 23rd of the individual parts. So I need to take my 6.75 times 10 to the 26 and I need to divide it by this. Now, whenever you've got this thing underneath the fraction bar, you need to either use parentheses or you need to use the EE button. The EE button will preserve it together as a whole. Otherwise, if you don't use parentheses around this, if you say like 6.022 times 10 to the 23rd, and you don't parentheses it, it's going to take this number, it's going to divide it by the first part, and then it'll multiply it by the second part. We don't want that. We want this whole unit under the fraction bar. So when I do that, I get actually quite a bit, quite a large amount of moles. There's a lot of atoms. So I have, we've got 3 sig figs, so 1,120 moles of sulfur. Going back to our handout.
Sorry, can I ask
Yeah.
a question about that?
Of
Do you
course.
say moles of sulfur or just atoms of sulfur? Because you took the moles out.
No, and this way we took the atoms out.
Oh, we did. All right. Okay. Sorry.
Yeah, no
All
worries. We started with atoms, we got rid of atoms, and we moved towards
Okay. All right. Sorry.
the last
I see.
problem. We went the other way. Yeah.
Okay. Thank you.
Mm-hmm. So we go back over to this sheet here. We've got some more. So I'm just going to have you guys do, let's do it for this one and this one. We'll do the compound ones. So how many moles of H2O are present in 5.43 times 10 to the 24th H2 molecules, and how many compounds, specifically how many molecule compounds are in 1.25 moles of NaCl. So you go ahead and work on those two. I'll give you about 4 minutes. All right. So I'm going to solve these on the whiteboard. So how many moles of H2O are there in, we know that we're given 5.43 times 10 to the 24th H2O molecules. Given, I want to find moles. So if it's molecules, it's the same thing as the individual elements. We start with our given, 5.43 times 10 to the 24th H2O molecules. And we know that we want to get into moles, so I'm going to put that on top, moles of H2O. I want to get rid of molecules, and then I relate them. So 1 mole, 6.022 times 10 to the 23rd. So in this way, we will be dividing by Avogadro's number. And we should end up with 9.02 moles of H2O. Same process if it's a compound. We're just talking about molecules. Next one, how many molecules were given? So we have 1.25 moles of NaCl. And I want to find molecules. All right, so we start with our given 1.25 moles NaCl, multiply it by, we'll multiply it by Avogadro's, but you can go through the process and put the mole on the bottom. 6.022 times 10 to the 23rd. Molecules, NaCl on top, the moles will cancel, we multiply those together. 7.53 times 10 to the 23rd NaCl molecules. So you may want to be asking yourself when you solve these, like conceptually, does it make sense? If I'm solving for a mole, you're not going to want some giant number. If you're solving for molecules or atoms, you better end up with a really large number. You're not going to end up with 4 molecules. Back over to the slides. We're going to talk about molar mass. So a molar mass is the mass of 1 mole of a substance. So if I have 1 mole of, I've got 1 mole of Na, 1 mole of Na. Its molar mass, or how many grams per mole, is going to be equal to 22.99 grams of Na. So a mole of something is like an everyday amount. Here we can see a mole of O2 is about what would fill a balloon, and it's 32.0 grams. A mole of water has a mass of 18 grams, and a mole of NaCl has a mass of 58.45 grams. Where are these numbers coming from? You have to have the molar masses memorized. No, molar mass is the same thing as your formula weight or your atom weight from the periodic chart. So these numbers that you've been using to calculate formula weight is the same thing as its molar mass. So looking at your periodic chart, what does 1 mole of carbon weigh? Should weigh 12.011. Okay, 1 mole of krypton, number 36, should weigh 83.80 moles per gram. The molar mass and the formula weight, those things are interchangeable. So I want you to calculate the molar mass for, it's the same thing that we were doing before, but calculate the molar mass for Fe2O3, iron 3 oxide. What is its molar mass? All right, so the mass for this should be 159.69 grams per mole, something like that. Another way to write this, you want to get in the habit of seeing it written like this, or I could write it as 1 mole of Fe is equal to, I'm sorry, Fe2O3 is equal to 159.69 grams of Fe2O3. So it's a conversion factor. Anytime we have conversion factors, it means we can jump from grams into moles or moles into grams. So let's do that. Here's some formula weights and molar weights. Okay, so atomic nitrogen, nitrogen is N, its formula weight would be 14, its molar mass would be 14 as well. So these are the same. This is how many atoms we would have in it. If we're dealing with nitrogen as far as its molecular or a diatomic, N2, that's a little bit different, right? So N2 has the mass of 2 nitrogens. Molar mass of 2 nitrogens. How many molecules? It's actually going to have 6.022 times 10 to the 23rd N2 molecules, or 2 times 6.022 times 10 to the 23rd nitrogen atoms. We can write that either way. If we're dealing with silver versus a silver ion, sometimes they add a little symbol in the corner to represent that there's like a small change. You don't really need to include that. It's pretty much the same mass. Barium chloride, we take into account everything to get the formula weight and the molar mass. Looking at this though, I want to go into this a little bit. So if we have barium chloride, I want to talk about its mole relationship because it doesn't, the slide didn't really talk a whole lot about that. Okay, so if we have barium chloride, if I have 1 mole of barium chloride, that means in every 1 mole of barium chloride, I have 1 mole of barium, right? Because there's 1 atom of it. It also means that I have 2 moles of chlorine, 2 moles for every 1 mole of the compound. You may be wondering, well, how can you have 2 of something in 1? Well, this is 1 molecule. This is 2 individual chlorines. So think of it like 1 chair has 4 legs, right? Or 1 clover has 3 leaves. Okay. So that is built into every single formula. So let's do a more complicated formula. Let's look at, should that equal be a plus? No, those are equal to each other, or they're equivalent to each other, and that we can use them as a conversion factor. So we won't be adding those together. So the way I want you guys to sort of be reading that is like this. 1 mole of this will produce or requires 1 mole of this. In order to make barium chloride, I need 1 mole of this to combine with 2 moles of this. So we're not necessarily adding them together. We're using them to be able to sort of hop around. What is their relationship? Like if you're making pancakes, I need 2 eggs for every 1 cup of flour. It's a 2-to-1 ratio. So think of a more as a ratio. All right, let's do, let's do Ca. I liked that one, Ca3PO4 2. Okay, so in every 1 mole of Ca3PO4 2, I want you to tell me how many moles of calcium you would expect, how many moles of phosphorus you would expect, and how many moles of oxygen you would expect, okay? Or what this is equivalent to. In order to make 1 mole of this, how many moles of calcium do I need? So pretty easy to calculate this. For every 1 of these packets, I get or need 3 of these. So it's 3 moles of Ca. For every 1 of these packets, I get how many P's? P with the 2 P's, okay? For oxygen, 4 times the 2 will give me 8. So 1 mole of calcium phosphate needs or yields 3 moles of calcium, 2 moles of phosphorus, and 8 moles of oxygen. Any questions on that relationship that's built into every single chemical formula? So these chemical formulas are not mass relationships. I'm not saying, hey, 3 grams of calcium combines with 2 grams of this. It's a mole relationship. It's telling me how many moles of each I have. That's one of the beautiful things about the mole. Sometimes we think of the mole as like the crossroads in chemistry because you can go from moles of one thing into moles of another thing really, really easily by looking at formulas and equations. Is that clear? You know, this chapter, this is a thicker chapter than some of the other ones. Real quick, just while we're at it. If I look at this formula right here, so I've got calcium nitrate. I'm going to write this over here. Calcium nitrate, CaNO3, 2. 1 mole of calcium nitrate is equivalent to, transitions to, is equal to, sort of, however you want to think about it. Well, we've got 1 mole of calcium, 1 mole of calcium. I've got 2 moles of the nitrogen, and I've got 3 times the 2 or 6 moles of oxygen. Hopefully that feels simple now. So converting from grams to moles, we're going to stop there. We'll do this next time. All right. If you have any questions, feel free to stay around. Otherwise, have a good weekend. Make sure you're staying up to date with homework and labs. We'll see you all on Tuesday.
Thank you.
Thank you.
Thank you.
Whoa. And if you don't need anything from me, drop out of the convo sooner than later, just so I can see who needs help. All right, I'm gonna put, Carter, I'm gonna put you in a waiting room and I'll bring you back in a minute or two after I talk to Jocelyn.
Hey, I'm sorry.
Hold on one second. Hold on one second, Jocelyn. Let me stop recording.